Hi guys. So today we're going to review all the solving that we have looked at so far this year. And we're just going to look at solving for all the different equations types that we have seen so far. So to start, there was quadratic. With quadratic, there were really three different methods that you could use. The first is completing the square, which is one that you may not remember. So the purpose of completing the square is to add a number to both sides that will give you a perfect square binomial. So if I were to set this one up, I would leave a blank and then I would move the one to the other side. The number that goes in that blank is the number that's going to make the left side of this equation factor into a perfect square trinomial. So what that would be is I take the middle number, I divide it by 2, and I square it. So that would be 4. That allows the left side to factor into x minus 2 squared. And then from here, it's an easier to solve equation. I can just take the square root of both sides and then add 2. So completing the square is a method that you will have to use next year when you get to conics. So it is important for you guys to be familiar with that method for solving. Quadratic formula usually is not easy, or usually not difficult to do. Typically I see the problems when it comes to simplifying, we tend to make mistakes. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a. So this one would be negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 6 all over 2 times 1. So this would be negative 20. And then from here, this is when you need to be careful with your simplifying. You cannot simplify those two 2's because it's not every term at the top that has the 2. You also cannot divide with the number in the square root. What we have to do first is simplify that square root. Any negative in a square root becomes an I outside of it. The square root of 20 simplifies into 2 root 5. That becomes 2i root 5. Now that it's simplified, we can take all of those 2's and simplify those, which would give me a final answer of negative 1 plus or minus I times the square root of 5. The other method you could use for quadratic is factoring. Any quadratics that you're solving, though, your first step needs to be to set it equal to 0. Then when you're factoring, if the a value is greater than 1, you need to show some extra work. You can't just find what multiplies to 36 and adds negative 12. That is part of our process, but it's not our final answer. So we're looking to see what multiplies to 9 times 4, what adds to the middle number, and those two numbers are negative 6. So what I do is I rewrite the problem by splitting the middle into the two numbers I just found. Now I can factor by grouping, so I cut it in half. 2x comes out, I'm left with 2x minus 3. I keep that sign, 3 comes out, I'm left with 2x minus 3. So the first set of parentheses is my first factor, everything else is my second factor. Then since I'm solving, I do have one extra step. I need to set each factor equal to 0. In this case, they're the same factor. So I would just do 2x minus 3 equals 0, and I get x equals 3/2. After quadratics, we looked at absolute value. So with absolute value, you have to remember you're typically going to set up two equations. But first, we have to get the absolute value by itself. So I would first subtract 1. Divide by 2. Then I need to set up the equation x minus 7 equals 5 and x minus 7 equals negative 5. I need to solve both of these equations. So I get x equals 12 and x equals 2. You always want to go back and plug those answers in back to the original equation, because a common thing you're going to see throughout these problems is the possibility of getting an extraneous solution. Both of these do work out. So those are both solutions. Let's go ahead and try number 2. So I'm going to set up two equations. 2x plus 18 equals 2 plus x. And I'm going to set up the equation 2x plus 18 equals, let me put it down here. 2x plus 18 equals negative 2 minus x, so making the entire other equation negative. So I'm going to solve the top. That gives me x equals negative 16. If I solve the bottom, that would give me 3x equals negative 20, and x equals negative 20 over 3. Now remember, we said we have to check for extraneous solutions. If I go back to the original and I plug in negative 16 and negative 16, then I would end up with my absolute value of negative 32 plus 18, which would be the absolute value of negative 14, which would be a positive 14. Over here on the right side, if I plug in negative 16, I'm getting that it would equal a negative 14, which is not possible. When you plug it back in, you're not going to have an absolute value equal to a negative number. So that is an extraneous solution, and that is an extraneous solution. So this one has no solution. On number 3, we can go ahead again and set up two equations. X plus 3 equals 4x plus 2. We also need to set up x plus 3 equals negative 4x minus 2 and solve both of these equations. So I end up with 1 equals 3x, so x equals 1/3, which if I plug it back in does work. And then I end up with 5x equals negative 5, so x equals negative 1. And if I go back and plug that in, that also works. So this one does have two solutions. Rational equations, there were two different methods that we could have used. So the first one with rationals is you could have cross-multiplied. So cross-multiplying, I would get 3 times 5x minus 2 is equal to 7 times 2x. So 15x minus 6 is equal to 14x, and I get that x equals 6. Again, I have to double check and plug that back in to make sure it's not an extraneous solution. Typically, your extraneous solutions for rationals will be anything that makes the denominator equal 0. Cross multiplying is easiest if you just have a fraction equal to a fraction, but something like number 2 where you're adding fractions, these are probably going to be easiest by getting a common denominator. So if I factor that middle problem, I can solve that to get my common denominator. So if you look, the left fraction is going to need the x plus 3, and the right fraction is going to need the x plus 2. So now I have x squared plus 3x over that common denominator So now that they all have the same denominator, since I'm solving, I don't need to go ahead and combine them together, I just need to solve the top. Because if the denominators stay the same, in order for this equation to work out, I just need to know that the top works out. So I'm just going to solve that top equation. This is quadratic, so I need to set it equal to 0. This factors into x minus 4 and x plus 2. Which means my two solutions are x equals 4 and x equals negative 2. But if I go back and plug in negative 2, I would be dividing by 0, so that is an extraneous solution. So my only answer is x equals 4. After rationals, we looked at radicals, so a lot of our root equations. Typically the goal here is get the square root by itself. And then once the square root's by itself, you can square both sides. So I get 81 equals 4x minus 3. And I get that x equals 21. But again, we need to plug this back in to check for extraneous solutions. If I plug that back in, it's not going to end up being an equivalent equation that is an extraneous solution. So this has no solution. Similar idea on number 2, except there's going to be a little bit more algebra with it. So first, I would move that over to get the square root by itself. Once the square root's by itself, I'm going to square both sides. When we square that binomial, we need to remember we're actually doing 3 minus x times 3 minus x, which gives us 9 minus 6x plus x squared. It's quadratic, so it has to equal 0. Let me go ahead and move that over. So we can factor, and I get two possible answers, x equals 5 and x equals 2. Plug them back in, make sure they're not extraneous. If I plug in 5, I get 5 plus the square root of 5 minus 1. That is not equal to 3, so 5 is not a solution. But if I plug in 2, that does work, and I do get an answer. I'm going to work out number 3 the same way, but 3 is going to have a little bit of extra steps just due to the way that it's set up. Because when I square this, I'm doing the square root of x plus 3 times the square root of x plus 3. So I'm actually going to FOIL that out, and I'm going to get x plus 6 square root of x plus 9. Since there's still a square root, I need to get that square root by itself again. So I get 6 square root of x equals x. I can go ahead and square these. Set it equal to 0. And this time I'm going to factor, but when I factor, x comes out, and it's just a GCF factoring. So I get two possible answers, and those answers are 0 and 36. If I plug them in, these are actually both going to work out. These will both be solutions in this case. All right, the last one is one very similar you guys had in a performance task a while ago that a lot of you made a little bit more difficult than you needed to. So again, goal here is to get the x by itself, so I'm going to add 14, divide by 2. And this time, to get rid of that exponent, I'm going to raise these to an exponent that makes it just 1. So I'm going to go ahead and raise this to the 4/3 power. That makes that just x to the first. But if I raise the left side to the 4/3 power, I have to raise the right side to the 4/3 power. So that becomes 27 to the 4/3. Remember, whenever you have those fraction exponents, it's simpler if you take the root first. So I'm going to take the cube root of 27, which is 3, do 3 to the 4th power, which is 81. And the most recent equations that we've done are exponential and log. There's really a couple different types of these equations, and right here we get an example of each one. With exponential, there's really two different ways you can solve. You can solve by getting equivalent bases if possible, otherwise you need to use logs. So on this first example, I can rewrite, and actually I think on your notes I changed that exponent to 8x plus 4. So it works out a little nicer. The square root of 7 I can rewrite as 7 to the 1/2. Then, once the bases are the same, I can just solve the exponents. So I get that 3x equals -4, so x equals -4/3. If I can't write them with the same base, then I need to solve by using logs. So again, I'm going to get the base by itself, so I'm going to subtract 7, divide by 2. And then at this point, I can rewrite this as a log. Since the base is e, I'm going to use the natural log. And then I'm going to add 2. And without a calculator, that's as far as you can go. With log equations, there's typically two kinds. And this first one, I have all logs. So what I'm going to do is I'm going to start by condensing the left side. Start writing log, and I change it to ln. If I'm adding logs, I multiply the arguments. That becomes 8x minus 28. Then if the logs are equivalent, all I have to do is set the arguments equal. So I end up with 7x equals 30. So x equals 30/7. On the second one, it's a little bit different. I'm still going to condense the two logs. When I multiply x plus 1 times x minus 1, I get x squared minus 1. The difference here is I don't have a log equal to another log. I have a log equal to a number. So I have to rewrite this one in exponential form. So 2 to the 3rd is equal to x squared minus 1. So I get that, we'll move it all this side, 9 is equal to x squared. So x is equal to usually plus or minus 9, but in this case, or plus or minus 3, in this case it's just the positive 3. Because a -3 would be an extraneous solution because it would give us a negative argument. Again, always double check for your extraneous solutions. Finally, these last three questions are actually factoring questions that can just sometimes be a little bit harder to see. So this is very similar to whenever we had some exponential equations and we had like e to the 2x minus e to the x minus 6 equals 0. And we plugged in a different variable to make it easier to factor. All of these problems can be solved the same way. On this first one, again, you can use any variable. I'm going to use u. And I'm going to replace 1 over x plus 1 with u. That makes this 6u squared minus u minus 1 equals 0, which is much simpler to factor. This is going to factor into 3u plus 1 and 2u minus 1, which means that u is going to be negative 1/3 and u is going to be 1/2. However, we don't care what u is. We're trying to solve for x. So at this point now, I would plug it back in, and I'm going to solve each of these equations for x. So I get negative x minus 1 equals 3. So negative x equals 4. So x equals negative 4 as one answer. And then x plus 1 equals 2. So x equals 1 as my other answer. This middle one's probably the hardest one to see. What I have to remember, if I have x to the 1/3 squared, I would multiply those exponents, which would be x to the 2/3, which is not what we wanted. Sorry, other way. If I let u equal x to the 1/6, sorry about that, x to the 1/6 squared would be x to the 2/6, which is x to the 1/3. So x to the 1/3 is actually my value here that I'm going to use. So when we rewrite this, this is 2x to the 1/3 minus 3x to the 1/6 plus 1 equals 0. So now I'm going to replace that. This is going to be 2u squared minus 3u plus 1 equals 0. So now this can factor. So my values for u would be 1/2 and 1. But again, I'm not solving for u, I'm solving for x. I'm going to plug this back in. So x to the 1/6 equals 1/2 and x to the 1/6 equals 1. To get x by itself, I would raise both sides to the 6th power. So this is 1/2 to the 6th power, which is 1 over 64. This is 1 to the 6th power, which is just 1. Finally, on the last one, same thing. I'm going to let u equal the square root of x, because the square root of x squared is just x. So now this is something that I can factor pretty easily. This is u minus 9, u minus 4. So I get that u equals 9 and u equals 4. So the square root of x equals 9 and the square root of x equals 4. So to get my final answer, I would square it and I get my two answers. All right, so everything else we're going to be doing these next couple days is just going to be a combination of all these solvings. Hopefully this is not too new for you guys, except for maybe these last three problems. But just remember all the strategies we've used so far this year, and always go back and double check your answers. Plug them back in to make sure, first of all, that they work, and second of all, that they're not extraneous.